Welcome back to this week's lecture. So this week we're going to discuss the classification and PySpark MLlib, which is machine learning library. So for students who have already taken the machine learning course, this week's lecture, especially today's lecture, would rather be a review or a refresh of your knowledge. So if you are really quite familiar with this part, you can skip it. For those who has not learned about machine learning at all, hopefully during this course, during this lecture, I could give you some basic ideas about how it works, or we will focus more on the procedure or the process of classification, and we will not focus on the machine learning theory behind those models. This is not the focus of this course, and if you are interested in CSE does offer a bunch of courses, machine learning courses, so you can enroll those courses if you are interested. Project 2 directly relates to this topic. We're going to use PySpark MLlib to implement a stacking model which contains multiple base classifiers such as naive Bayes classifier and SVM, as we will introduce in today's lecture or Wednesday's lecture. As I said, we will mainly focus on the process of classification, and let's start from the PySpark MLlib. So the MLlib is Spark's scalable machine learning library. So it consists of some common learning algorithms and utilities. So below is a list of the major components in MLlib. So basic statistics includes the most basic of machine learning techniques, like summary statistics, for example, the mean, variance, max, mean, and number of non-zeros, these methods. The correlations is to show the correlation between different data sets. Sampling includes sample by key and sample by key exact and other sampling methods. Hypothesis testing, for example, like chi-squared test. Random data generation, like you can generate random data following different distributions, such as uniform distribution or normal distribution or Poisson distribution. This is basic statistics. Classification is the problem to identify which of a set of categories that a new observation belongs. We will introduce more on classification. Regression is a little bit like classification. They do have differences, which we will discuss later. So it is a statistic process for estimating the relationships between among variables. Clustering is the task of grouping a set of objects so that the objects in the same group are more similar to each other, and if they are in different groups, they're more likely to be dissimilar to each other. So k-means, which we have introduced, I think it's last week Yeah, it's a very common used clustering algorithm. Recommendation system is information filtering system that seeks to predict the rating of that a user would give to an item. For example, in the online shopping systems like eBay, or the, for example, the movie rating web pages like IMDb. So basically, a user can rate, can give a rate or give a score to a bunch of items, and the recommendation system is to predict whether for an item, well, to predict the rate or the score that a particular user would give to a particular item, right? Dimension reduction is the process of reducing the number of random variables under consideration, such as PCA or SVC. Feature extraction starts from an initial set of measured data and builds derived values or features intended to be informative and non-redundant, and this is used in machine learning tasks, and also sometimes it is used to help human to interpret to help the human interpretation of the data, and the optimization part is very important in machine learning. So basically, in most cases we need to optimize the objective function such that we can. This is also known as a train classifier, and so this part contains a bunch of optimization algorithms such as SGD, and this is basically the major components of PySpark MLlib. It is more or less like a Spark version of sklearn if you have used that before, right? And in our class, in our course, we will focus on classification part, as this is one of the most commonly used techniques or the topics in machine learning. All right, so let's look at so classification, right? So basically, classification, or the task, is to predict a categorical class label. This class labels can be anything. Like, for example, I give you an image and I wanted you to tell me if it is a dog or not. That is a classification problem. And for example, I give you a document and you tell me, well, the topic of the document is about sport or not. Or these are the binary labels, examples of binary labels. And we can also have multi-labels. For example, I give you a document and I want to know if the type of the document is say an email or an article or a news or something else, right? These are the so class labels could be anything, depends on the problem itself. Right? So in order to do this or achieve this goal, we need to construct a model based on the training set or the training data, and the values, which is the class labels, which are also parts of the training data, in a classifying attribute. So the class labels will be treated as a part of a classifying attribute and use it in classifying new data. So the idea is we construct a model and we use it to classifying new data. And in order to construct the model, we will use the training set and the class labels. And prediction or regression is quite similar to classification, but they do have different objectives. And for prediction, the model is, or the prediction model is to model a continuous valued functions such that they can predict unknown or missing values. So an example of prediction or regression is a linear regression, which say we have these points and we want to find a linear, say a linear function that is y equals to ax, such that we can best fit the points here. So the line would be something like this, and with this function, with this learned function, we can predict the unknown values. For example, when x equals to x1, we would know the corresponding y1 based on the learned linear function. So, and for classification, it's different because classification, what we predict is the class labels. So you would take an item or an object and you predict its label. So the application of classification is quite wide. It can be used in different areas, and it has been used in many real life applications. Right. For example, in medical diagnosis, I think the IBM has initiated this project quite a few years ago. So basically, the computer or the classifier would help you to review your decisions and help you on diagnose what happened to the patient. And credit approval, basically the bank would have all your information, not all your information, would have your relative informations when you apply for a loan, for example. Then it will use a classifier to decide whether your credit is okay or not, or whether it can they should give you the chance to apply the loan or not, right? And natural language processing, that is a big area. So you can analyze the text files, or you can label them. You can do sentiment analysis. You can assign labels to each and every document or sentences. For example, the labels of its type or of its topic, or even, the author. You can do the prediction, right? And this is also one of the most popular research topics in recent years. That's all because of the fast development of machine learning, right? So that is also why we include this machine learning library in our course, because with high probability you would need to use it. I mean, it's kind of like the trend of the development of big data. So eventually we will use big data to solve real world problems, and machine learning, or especially classification, would be one of the most powerful weapon that we can use. So that's why we kind of make this a new content in this course, right? And to give a formal definition of the classification problem. So the problem is defined as, given a new object O, we want to map it into a feature vector X. So X is a vector, and X is we usually consider it's in a Euclidean space, right? And we predict the output, which is the class label. So Y is one label, the predicted label, and this big Y is the set of all the labels. And for a binary classification, as we have mentioned before, you basically have this big Y contains two elements. So it could be 0 or 1, which can refers to false and true, for example, or it is usually refers to false and true, but the meaning of false and true can be different, depends on the application. For example, later you will see in our example, we say that 1 corresponds to the topic is sport, say, and the 0 is the topic is not sport, right? And you can use sometimes you can use a -1 1. It really does not matter. It really does not matter. And multi-class classification, you can have this big Y is a set of 1, 2, 3 until C, which is you can think it as different class labels, right? And also this we usually use integers here, but it's not compulsory. I mean, you can use strings or whatever, but arguably using integers is more easy to process, right? And in many classification models, where we need to write the loss function, which we may not see in this course, but when we write the loss function, if y is in 0 or 1, then we can directly use y. Otherwise, we need to convert a label into 0 or 1 when we use it in the loss function. So in order to do this predict thing, we need, or essentially classification is all about learn a classification function. Right? So the function fx would take the x, which is the feature vector x, as the input. Right? And it will output a y, which is in this big Y. So this function is from is to project to map a vector in Euclidean space to a label within the label space or the label set. And for regression, if you still remember, the difference is that it actually maps a vector in Euclidean space into a real number, a real number. So basically, it is to estimate the value of fx, as the example here. In this case, this x is just a number, right? But you can imagine for the higher dimension cases where it becomes a vector. So that is still maybe too dry for some of you. So let's start. Let's look at an example of classification, which is text categorization. By the way, this is also the topic of project 2 as well. So the example here would hopefully it would also help you understanding project 2, right? The task in project 2. So basically, in text categorization, you would be given a document or a sentence. We usually all use document. I mean, or say we view a sentence as a document as well. So basically, this is an example of the document, and yeah, from the text in this, you probably can guess the topic. So the objective is to predict the topic of the document, and the topic would be in the predefined labels. So if we consider a binary classification problem, so the labels would be if it is politics or not. Right? If it is multi-label classification, so it could be politics or sports or entertainment or other, right? Different topics. So this is kind of like the input and output of the problem, right? And in order to do that, we need to learn the classification function, right? Which is fx here. So in order to learn this, we will need to firstly convert this example or the task into an abstracted mathematic format, right? So basically, we need to know what is x here, what is y here, and what this f would should look like. And well, so the first question would be how to convert a document to a vector, and the second question would be how to convert the predefined labels to this y. So the second question would be easy. I mean, for example, politics or not. So we can define 0 as not politics, and 1 would be politics. Right. And and for x, for this feature vector, it's a little bit more complicated, and also we do have different approaches or different choices on how to do this. And well, this is a big topic. I mean, if we really put some time on discussing about this, but again, this is not directly related to big data or this course. So we would, I mean, for the following of today's lecture, including lecture in next few lectures, sorry, the slides in the next few lectures, we will use very simple say feature vector generation method, which is also known as bag of words. So that is we will talk about that later. But here I do want to point out that you would have different, you could have different choices for different types of input data. So here the input data is document, or more or less a text. So you can use a bag of words, for example. So essentially the idea is just to take the frequency of the words. And for example, if the input is let's say an object, say a human being, let's say, you would have to extract feature from the human being, from the person. Yeah, let's say the application would be a medical diagnosis, for example. So you probably want to know its her height, weight, age, right? Where she lives, what's her usual exercise, right? And blah blah. I mean, depends on what you're going to predict, and this is also called feature generation. So basically, you take the input and you output a feature vector. All right, and all right, so this problem is essentially, if we abstract it again, it would be like the input object is a sequence of words, which is a document, and we convert it into X, the feature vector. Okay, we use a bag of words representation. So basically, we use the frequency of each word, and the word here comes from the vocabulary. So the whole vocabulary. That's why you would see that Trump, for example, is also a word that you need to consider with, although the frequency of Trump in this document would be 0. And you would finally get your feature vector, which is just the frequency of different words. For example, this 2 could correspond to Morrison, and this 0 could correspond to Trump. Yeah, you would have for each element or each integer here corresponds to the frequency of a particular word in the vocabulary. So that's how you get the input feature or the input feature vector X. And the class labels would be this big Y. So you assign 1 to politics, or -1 or 0 to not politics. Right. So to summarize this again, I mean, you need to always remember, given you a problem, you need to when you convert it into a classification problem, you need to know what is input and what is output. And especially, I mean, for input, you need to know how to generate the input feature vectors. That is a critical step. And for output, you need to know what are the class labels. Arguably, I mean, the output part is easier, and the input part would require more efforts. All right. And just to take another small example, for example, the image classification, where the input would be a matrix of RGB values. So basically, an image would have, for example, the image of this size would have pixels, right? And each pixel is represented by an RGB value. So you would have a matrix. So each cell corresponds to a single pixel, and the value is its corresponding RGB values. You need to convert this input into input feature vector, which here, in this example, we can use a color histogram. Say how much, say how many red pixel are there in this image, how many blue pixel in this image. And you can also use other different feature vectors. For example, currently in neural network, many of the methods just directly use the input, or with very minor modifications of the original input matrix and use this as the input. So that is or the input feature vector. This is also doable. It depends on the model you use. All right. And the output is the class labels. So basically here we want to know if it is a building or not. So if it is a building, then the label would be 1. And if it is not a building, the label would be -1. All right, so hopefully by now, with all these examples, you would have already known that given you a real application or a real problem, how do you convert it into a classification problem? Right. So basically, you need to know what is the input and what is the output. That's the two essential things for now. And all right, so another thing, right? Let's say let's discuss this under the assumption of supervised learning. So the case would be different for unsupervised learning or semi-supervised learning, but we don't because of the time limitation and also it is not directly related to big data. So we will only discuss supervised learning in this course. So basically, as you may have noticed, we have discussed about input data. We have discussed about feature vectors and the class labels, which is the output data. So what is left is this fx. And this is the most important issue when we train a classifier or when we solve the problem using machine learning or classification techniques. So how to get fx, right? Well, in supervised learning, we are given a set of training examples. Right? So this training examples is a tuple or a pair of feature vector and class label. So xi would be the feature vector, and yi would be the class label. Right. So for I from 1 to n, which n is the number of training examples or training data. Right. And there is a very important assumption, which is also a critical assumption for machine learning theory. So it's about, so the assumption is that all these training examples, they are identically and independently distributed in the training data. Means they all have the same distribution, and the two training examples are independent from each other. So this independence property plays a role as a useful working modeling assumption that allows us to derive learning methods. It is a sufficient but not necessary assumption for providing consistency and providing error bounds of in machine learning theory. It is also a sufficient but not necessary assumption for using random data splitting techniques such as bagging for learning, and also use cross validation, which we will discuss later, for assessment. Right. This topic is also, this IID assumption topic is if we are going to dive into this, it will occupy too many time. So we will skip it. Just leave it as for now. Basically here I just need to mention it because it is a critical assumption for machine learning theory. So I should mention it here. So as long as we have D, now what we need to do is that we use D to learn fx. So this is about supervised learning. So you use training examples or training data to learn fx, or more specifically, to learn the parameter of fx. For example, if fx is simply w transport x plus b, then what we do is we use D to learn w and b. So w and b are the parameters of this model, the fx model. All right, so I would really like this example. I mean, machine learning is just like learning, or you when you try to learn something, or you attend a class, or more specifically. So the training examples were the say the lecture slides or labs, or the materials or resources that you obtain from internet. You use this thing to train yourself. So yourself is a model. Right? Yourself is a model, and you use this thing to train a model. And the model, what the model can do is that given a test, or given a feature vector, which can be a question in your final exam, you can predict the label of this x, so which is corresponds to the answer, your answer to this question. And many of the terminologies and the processes that we are going to discuss later, you can all fit that into this example, or this analogy, to help you understand how the whole things, right, or how it works. All right, so some machine learning terminologies. So supervised learning has input labeled data. So number of instances are the this is the n in the previous slides. Number of attributes, this is see the size of x. So the input, should be size of x plus 1. So the input labeled data would be a matrix. Right, so the size is n times the size of x plus 1. So the number of attributes is the number of features, which is x, the number of features, plus 1. This 1 is for the class label, right? Because this is the input labeled data, or it is also known as the training data. So it has the class label with it. That's why it is called supervised. So you can use this labeled data to help you. It's more like the sample solution, right? You can use it to help you train your model. So labeled data is split into 3 or 4 disjoint subsets. There are training data, development data, and testing data. So training data is used to build a classifier. Development data is used to select a classifier, and testing data is used to evaluate the classifier. So if we take a high school student as an example here, say the high school student would be the model. All right. So the training data would be the courses that he takes, and the homeworks, for example, or the say those online resources that he can obtain. So basically, all these things the questions comes together with the answers, right? So the students can use this to train the model, to train or to prepare himself, right? And development data would be like, the exams in each term that is organized by school, right? Or even the NAPLAN exam. I mean, these are to help the students to adjust his model, right? To help him realize that the model or the classifier is not good enough, right? And all this is to serve the purpose of the testing data, which is the HSC, right? So all the efforts here is to help him or prepare him well for the final testing, which is HSC, that is corresponds to the evaluation, right? So to evaluate the classifier, or in that example, to evaluate the high school student. All right. So the output of the classifier for binary classification, the number of labels equals to 2, and for multi-label classification, the number of labels is. And as we have discussed, as we have mentioned the evaluation of the classifier, so how to evaluate the classifier is very important, as you can use the same way to evaluate the classifier within the using the development data, and then finally when you are dealing with the testing data, you would have better prepared for the testing data as well. So the evaluation criteria is important here. So in order to evaluate the classifier, we need the terminology that has been used here. First of all is the false positive, false negative, and true positives. Right. Basically it is the same, or at least similar concept to that has been introduced in the lecture of LSH, and also the assignment questions. And okay, false positive. In order to know what is false positive and false negative, we need to define what is positive and what is negative first. So it is about the label. It is all about the label. So let's consider the binary label first. So, for example, the binary label would be either it is politics or not politics. So we take politics. Sorry. We use politics as positive, and non-politics as negative. This is for a binary label, because binary label usually it has a yes and no, or something like this. And for multi-label classification problem, so it's a little bit more complicated. So for example, if we have say we have politics, sports, and other. In order to compute the false positive, false negative, and precision, recall, so on, we need to decide what is positive first. So what we do is we select one of them as positive. For example, we take sports as positive, and everything that is not sports, which is politics or other, so this would be considered as negative, as negative. And in this case, the precision and recall, which we will explain, we will explain later, but the precision here is the precision of sports, and the recall here would be the recall of sports. So apparently you would have a precision for politics as well, and for other as well, and so and the same as recall. Then you need to aggregate the 3 different precisions and recalls as well. So this is in order to do that, it involves the concept of micro and macro precision recall and F1 score. So we will discuss this later. So back to here, as long as we know what is positive and what is negative. All right, so false positive would be that should be negative, but classified as positive. For example, not politics, but classified as politics. So the positive here is the predicted result or the predicted label, and false indicates that the prediction is wrong. So for the same reason, the false negative is the thing that is positive but has been classified as not positive, as negative. For example, the politics but classified as not politics. And so again, negative is the classification result, and false indicates that the result is incorrect. And true positive is the positive that is classified as positive. So precision would be TP, which is true positive, divided by TP plus FP. So this is among all the predicted as positive samples or testing data, how many of them are true, right? So it's like among all your predictions of positive, how many of them are really positive? So this is a precision. A recall would be TP divided by TP plus FN. So remember, FN means those things should be positive. So recall is that among all those things that are indeed positive, how many of them are labeled as or predicted as positive? So this is recall. And for F1 score is just the harmonic mean of precision and recall. All right. So with all these definitions are clear here, back to micro and macro, say micro F1 and macro F1. Right. So micro F1 would be, you take each and every element in the testing data. So its true label would be positive, and anything that is not its true label would be negative. And then you can compute, based on this, you can compute the overall precision and recall for all the data. So that is micro F1. Micro in the sense that you take each test sample as a unit. And for macro F1, it is just the mean of F1 for each and every class label. So it means you compute the F1 for politics, you compute the F1 for sports and other, and then you do the average of these 3. Then you get the macro F1. So macro here stands for you take the label or all the testing data with the same label, as a unit to compute precision recall and F1. Well, this micro and macro F1 is maybe a little bit too complex for this course, and again, it is not the essential part of this big data course. So if you are interested, I mean, you can. These are very common definitions. You can search for the keywords, and you can see materials in the internet. So let's quickly move to next slides. So in order to conclude this whole process of classification, so we summarize it into a two-step process. Although the real case would be much more complex. All right. So let's start from a simple, more abstracted way to see this classification problem, and later we will see it in detail. So as a two-step process, there are classifier construction and classifier usage. And classifier construction is arguably more important, as each tuple or sample, which is xi, is assumed to belong to a predefined class, that is yi, as determined by the class label attribute. And the set of tuples used for classifier construction is training set. And the classifier is represented as a classification rules or decision trees or mathematical formulas. So that is also known as a model. So basically, what the classifier looks like, or what this function looks like. There are different ways to represent a classifier, and in this course we will focus more on this mathematical formulas, or say, for example, a naive Bayes or SVM or linear logistic regression. All right. Anyway, so after all this, you would construct the classifier, or you have trained the classifier. The detail will be discussed later. And for the classifier usage, you classifying feature or unknown objects. And also we need to estimate the accuracy of the classifier. So in order to do that, the known label of test sample is compared with the classified result from the classifier, and the accuracy rate is the percentage of test set samples that are correctly classified by the classifier. In this case, this accuracy rate is another evaluation measurement. Would be true positive plus true negative divided by you plus everything together, right? And test set is independent of training set, otherwise overfitting will occur. Overfitting is another important concept in machine learning, and anyway, due to the time limitation, we can't explain this in detail. So basically, overfitting is that overfitting is that the generalization of your classifier is not good. So it means that you can think of, say, if the students memorize, for example, if the students memorize all the questions in the textbook, right, but just memorize without any understanding, would the student be able to achieve a good mark in his final? Apparently not, because there is no generalization in this student's study, right? So that is known as overfitting. So basically, you focus more on the training examples, and you ignore the generalization. And for when the testing data comes, you see a different one. You don't know how to deal with it, or you deal with it poorly. All right, so this is called overfitting. And okay, if the accuracy is acceptable, we use the classifier to classify data tuples whose class label are not known. Means in this step, you kind of use your classifier in real world applications. All right, so let's stop here and have a break. We will come back and look at the classification process in more detail.